All right, so we're going to talk a little bit about parametric equations and how they fit into FRQ questions. So we just finished up a unit on this, so this should be fairly fresh in your brain. But typically what's going to happen when we have a parametric FRQ is that you are going to be given a parametric function, and it could be in vector form, it might not be in vector form, but it usually will represent the position of a particle. And so we'll call that position x of t, y of t. And this could be the initial information, or it could start the problem with a derivative. And the derivative would represent the velocity, which would be x prime of t, y prime of t. It could also say, instead of x prime and y prime, it could just say x, or dx dt, dy dt. And I'll just, again, go to one more derivative here for acceleration, which would be the second derivative. These questions are almost always calculator questions. But you don't have to be necessarily in parametric mode. You can easily do all of these calculations using the function mode in the calculator. A couple other very direct, straightforward formulas. Again, these should be fresh in your memory from your last test. Would be the speed equation, which is the square root of x prime of t squared plus y prime of t squared. And if you're asked for total distance traveled, or they could call that the arc length. To find that, we do the integral of the speed. It's the integral from a to b of the square root of x prime of t squared plus y prime of t squared. Okay, so those are just basic formulas. When questions are asked about these, it's a matter of knowing the formulas and then just kind of plugging stuff in. Now let's move on to another thing that could come up. You could be asked to find dy dx. Now if you're asked to find dy dx, you would do y prime of t over x prime of t, and then you would plug in a t value. So what this would give you is this is going to give you the slope of a tangent line at a t value. So you would plug a specific t value in. So that's the first route, and that's something we covered in our last chapter. But every once in a while in the AP exam, not so much in an FRQ, but you'll see a multiple choice question that will ask you for the second derivative. That's the second derivative of y with respect to x. And we'll practice this a little bit more as we get closer to the AP exam. But there's a formula for how to do this. And you would take the derivative with respect to t of dy dx. And of course dy dx is y prime over x prime. And then you divide that by dx dt. Okay, so dx dt, again, that's just x prime of t. So it would just be a matter of finding this. So this is a potential multiple choice question on the AP exam. Now, a couple of applications to motion that they could ask you about. One thing that could come up is they might say, when is the particle at rest? If you're asked about when the particle is at rest, that means there is no movement in the horizontal or vertical direction. So this would be where x prime of t equals 0 and where y prime of t equals 0. This is a very common kind of question you could see. You may be asked about a horizontal tangent line. Where would the tangent line be horizontal? If we look back up at our slope of our tangent line, if we want that to be If we want that tangent line to be horizontal, that means the slope is equal to 0. So that would mean dy dx equals 0, which implies that y prime of t equals 0 and x prime of t is not 0. So you have to make sure you verify both of those things. Another thing about motion, could talk about whether the particle is moving left or right. If you want to analyze that, you have to look at the sign of x prime of t. Positive equals moving to the right, negative equals moving to the left. And if I can analyze left or right movement, I can also analyze up or down. And we can also analyze up or down. That's going to come from the sign of y prime of t. So for the sign of y prime of t, if it's positive, that means the particle is moving up. If it is negative, it means the particle is moving down. Okay, now one other big thing, and this is a very common question if you get one of these parametric FRQs. And this piece is about finding an original coordinate. So let's say you're given x prime of t and y prime of t, or just one of them. Given that, find the x and y coordinate at a specific t value. Okay, so this, if you have a problem like this, you are not going to be given equations for x and y, only the derivatives. So let's do a quick example. Let's say, for example's sake, that you are given that x prime of t is equal to 3t plus 1. And the question might say, find x of 2 if x of 0 is equal to negative 1. Okay, so what happens with this is that when it just says like find x of 2 or x of 0, what that means is that's looking for a coordinate. So this right here is looking for the x coordinate at t equals 2. This represents a known point. Okay, so we're going to use this known point. And the way that we're going to do that is we're going to do an antiderivative. We're going to use the integral here because we have to go from the derivative back to the original function. So if I think of doing the integral of x prime of t dt, this should give me back x of t. But there's a way I can do this without going through the process of finding plus c and actually not even having to deal with the antiderivative. And the way I'm going to do that is by setting up a definite integral instead of an indefinite integral. You'll notice we've got these two t values, 0 and 2. I'm going to make those my endpoints. Then when I do the process of this definite integral, I take the antiderivative of x prime of t, which is x of 2 minus x of 0. This should, of course, look familiar. This is the fundamental theorem of calculus. This allows us to find x sub 2 without having to do an antiderivative. So what would happen is this number you can find on your calculator. X sub 2 is what we're looking for, and then you could plug in negative 1 for x sub 0. So I'll just say this is some number, and that would equal x of 2 plus 1, because we're doing a minus a negative 1, and then we can solve for x sub 2. So that is something that is likely you'll be asked to do on every single parametric FRQ that you get. So with this information, you are all set to do a parametric FRQ.